First we'll look at the complement law proof using an OR gate where A or not A equals 1. So we've got an OR gate and the inputs to it are A and not A, and one of those is always going to be 1. When A is on, not A is off. When A is off, not A is on. So one of them is always on, so the output is always true. So A or not A is always logic 1. Proving the absorption law using logic gates and a truth table where A or not AB is the same as A or B. So we've got the circuit for A or not AB, and we've got the inputs A and B which count from 0 to 3 or 0, 0 to 1, 1. We have an AND gate for the not A ANDed with B, and we have an OR gate for A ORed with not A and B, and we want to prove that that column is the same as A or B, which would be 0, 1, 1, 1, where the OR function is true if either input is true. So when both inputs are low, not A ANDed to B is low, so the OR gate output is low as well, because the OR gate has no inputs that are high, so it needs one of them to be high for the output to be high. So far A or not AB is the same as A or B, but we need to prove it for every case. So when the inputs are 0 and 1, A is high, so the output goes high through the OR gate, but not A and B is low, but that doesn't matter because A or not A and B is high. And that follows what an OR gate would do, a 2-input OR gate. So far they're true. The third case where B is high and A is low, not A ANDed with B goes high now. So the OR gate has one logic 1 signal on its input, so the output is high. So far A or not AB is the same as A or B, but we need to prove it for every case. Now both inputs are high, and so long as A is high, the output will be high through the OR gate. So this proves that the two expressions are the same and can be interchanged. A or not AB is the same as A or B, so we're saving ourselves some logic gates. And this is just a quick animation to go through the truth table a few times. We can have multiple ANDed variables in the second term, and only the single complemented variable disappears. So if Q is A or not ABC, that's the same as A or BC. So it doesn't matter how many terms are ANDed in the second term, only the complemented one disappears, and we'll talk more about that in a second. I'm going to design a full binary to hexadecimal decoder using Boolean algebra and using negative logic. So we're looking for when the output is low because it's often more efficient and quick. So this table shows us when the segments are lit or not lit for all counts from 0 to 15, and we're going to use negative logic. We're going to focus on when the outputs are low because there's less cases to deal with and less Boolean expressions. So for not A is these 5 states, whereas there was loads more when A was high. So we can find the expression for not A and put it through a NOT gate and get the expression for A. So the first state when it's low was not D, not C, not B, A, or not D, C, not B, not A. And we just go through the table making Boolean terms to find a Boolean expression for not A. And I'll show you how to wire it up. So that's the last case when it's low. And the last two terms have common factors of DC, not B. So that's the complement law in terms 4 and 5 there, where the value of A doesn't matter, so it's redundant, so we can get rid of it. So that's DC, not B, as a common factor. Term 4 has not A, term 5 has A. So that means it doesn't matter whether A is high or low. So it's redundant. So the complement law gets rid of it. So then we just write it out again. So it's going to be or DC not B. And then we're always looking for similarities and differences. The second and fourth terms now both have not B and C as a common factor. We have D or not D not A, which is the absorption law. So those two, if I want to see what they're worth, we have the common factor of not BC, or we could have said C not B. And then the other terms are D or not D not A. And remember the absorption law, A or not AB is A or B, so you get rid of the complemented variable in the AND term. So those two terms are worth B not C into D or not A, which is not BC D or not BC not A. So then we regroup and write what we have for the overall expression not A. The first term, not D not C not B A, or the equivalent of these two that we use the absorption law on. Write those down. D not C B, I'm doing it in alphabetical order usually. So there's the expression for not A, and we're going to tap off from the counter logic like before. And instead of using an OR gate, which gives us not A, we could use a NOT gate after to give us segment A. But an OR gate followed by a NOT gate is a NOR gate. So we can use negative logic with a NOR gate to get the correct output. Now we're looking at when B is low, because there's less cases than when it's high. So not B is those 1, 2, 3, 4, 5, 6 cases. So write down the Boolean expressions. The fourth one is DC not B not A. The fifth one, DCB not A, and then DCB A. So you can see the complement law in the last two at least. I'll number them, make it a bit easier to keep track. So in terms 2 and 5, we've got B and not A and C as common factors. So it's the D that we apply the complement law to. So we have CB not A multiplied by 1, because that's D or not D. So write out the expressions again with any changes that we've made. Get rid of those two terms and replace them with the overall output that we created with the complement law. And then write down any existing terms. And look at those for similarities and differences. So terms 3 and 5, we have common factors of DB and A. So it's the C that's a redundant term from the complement law. Then clean it up again. Those two terms gave us DBA. But you only need to write D and B and A once. Label them again. The second and fourth terms, can you see anything? We've got C and not A in both terms. So they'll be the common factors outside the brackets. So that is the absorption law. In the bracket is B or not BD. So that not B is going to disappear. So we end up with C naught A into B or D. So that's C naught A B or C naught A D, which you can write in alphabetical order if you want to. So we've used the absorption law, CB naught A or DC naught A. So we'll cross them off, use the two that came as the output from the absorption law and regroup. So not B is equal to not D, C, not B, A, or we already had DBA, or the two terms that we just came up with from the absorption law, CB naught A or DC naught A. I usually cross them off as I've written them down so I don't duplicate and bring things back into the expression. And that is it for not B, because we don't have enough differences or similarities to use any more laws. So we're going to put those through a NOR gate and give us segment B. Now for the expression for not C, because there's only 4 cases when C is low, so we should focus on those instead of all the other cases when it's high. So that is negative logic. So we've got not D, not C, B not A, or DC not B not A, or DCB not A, or DCBA. So immediately we can see the complement law in the last 2 terms. So I'll highlight them, number them. So terms 3 and 4, complement law, because they both have DCB and they have A or not A. So the value of A doesn't matter because both terms are true. So A is redundant through the complement law. So just write out again what we have now, or DCB. So what are the commonalities here? So we've got the last 2 terms. We've got DC as common factors. Then we've got B or not B, not A. So that is the absorption law. So bring out the common factors, D and C into not B, not A on the second term, and just B on the third. But because the complement is in the ANDed term, we get rid of not B and then multiply out. So that's going to become DC into not A or B, multiply out, DC not A or DC and B. So C is equal to not D, not C, B not A, or those other 2 terms. And there's no further simplification that we can do. So that is the output for not C. Put it through a NOR gate and it gives us the output for segment C. Because if you have odd terms and then they are negated or complemented, that's going to give us a NOR gate to give us the output for C. Now to find the expression for not D, because there's only 6 out of the 16 cases where it's low, we'll use negative logic. You can flip between positive and negative depending on how many terms that you have to deal with. I'll just write down the Boolean expressions for these 6 terms. The last one is DCB, A all ANDed. So numbered them, terms 1 and 4. Do you notice anything about them? Not C, not B, A in both terms. So the value of D is irrelevant to those two terms being true, so the complement law gets rid of them. So we have not C, not B, and A, which accounts for terms 1 and 4. Then we write the others down where they were, so we don't forget about them. We're always looking for similarities and differences, so these two terms, again, it's the complement law, where the value of D is irrelevant. So they both turn into C and B and A, or CBA. Or CBA, get rid of those two, or whatever was there before. And now for output not E, we've got 1, 2, 3, 4, 6 different states when segment E is low or not E is true. Write down what they are. So we're just looking at the binary values on the from the counter, and the last one, D not C not B A. So we're looking for similarities and differences. You spotted any? So terms 1 to 6, it's good to label them so we can refer to them. Terms 1 and 2 are the same, apart from one of the variables. So they have a common factor of not D, not C, and A, and it's the B that's redundant in those two. And then we continue looking for more. Terms 3 and 4 have D, C, not B in both terms. So it's the A level, logic level, that's irrelevant. So the complement law knocks out the A term in that one. Now with this term and the third term, they have not D and A in common. Then we have not C or CB. So that is the absorption law. Not D, A is common to both. We have not C or CB. So it's the C that we get rid of with the absorption law. So then we just multiply out to what's left. So not E is equal to the first term, not D, not C, A, or the other part of the absorption. What we had anyway, not D, C, not B, and the last term, D, not C, not B, A. There's one more thing we can do. Have a stare at it. Have you spotted it? The first and the last terms have common factors of A and not C, or not CA. So you've got A not C multiplied by not D, or D not B. So that's the absorption law again. Get rid of the complemented term in the ANDed variable. That's A not C not D, or A not C not B. So not E is equal to just got rid of those two from the absorption law and replaced them. Not C, not B, A. Cross them off when you've accounted for them. Not D, B, A, or not D, C, not B. And that is not E. So the segment E, when we put it through a NOR gate, that's the expression that we'll use. Now we'll move on to not F, because there's not many cases when F is low, so we'll focus in on those. 2, 3, 4, 5, and 6 states when F is low. Write out the Boolean expressions. I wish I'd crossed them off earlier to make it so much easier to keep count of where I am. Cross that one off. Then not D, not C, B, A. Or not D, C, B, A. Cross that off. Or D, C, not B, not A. D, C, not B, A. So there's the complement law in the last two. And in the third and fourth, we've got common factors, and we can complement out the value of C, because it doesn't matter whether C is high or low, because both terms are true. So the value of C is redundant from the complement law. Then those two both have DC and not B. So it's the value of A that doesn't matter. So they reduce to DC not B. Then include the other terms that we haven't touched yet. B not A. We're looking for commonalities and differences. So in the first and third terms, we have not D and A as common factors, and we have B or not B, C. B or not B, not C, I should say. So that's the absorption law. Bring out the common factors. That goes into not B, not C, or B. So it's the not B that we need to get rid of, because that's the complement in the ANDed term. Then multiply out. Not D, not C, A. I'm just doing it alphabetically if you don't have to. Then not D, B, A. You notice with the absorption law, it's only one of the terms that actually changes, but I still write them out again afterwards to show what I've done. So we've got not D, not C, A, or not D, B, A. Cross those two off. Bring the others down that we haven't touched in a while. Or D, C, not B. But there's more that we can do. The first and third terms now have common factors of not D and not C. We've got A or not A, B, and that is the absorption law again. So we've got not D, not C into literally A or not A, B, which is the way that we learn the absorption law. So the not A is the imposter, so we get rid of the not A and then multiply out again. Or not D, not C, B. And then regroup. Not D, not C, A, or not D, not C, B, or not D, B, A, or D, C, not B. And that is the minimized expression for segment not F. Put it through a NOR gate, it gives us segment F. Finally, segment G. We're going to use not G because there's not many times when it's low, and this is going to be quite simple. 3 different states. The first two, you can see we have the complement law anyway, just looking at the truth table. Values. so the value of A doesn't matter in the first two terms, because we have common factors of not D, not C, not B. They're both true, so A has no effect whether it's high or low, and that's what the complement law is about. So that is worth not D, not C, not B, or the other term, the final term, which was not D, C, B, A. And that is the minimized expression. There's nothing else we can do. So we're ready to implement this and make our full HEX 7-segment decoder on Proteus. So implementing the full binary to hexadecimal 7-segment display decoder using Proteus, having learned Boolean algebra. So I want to show you something. If you right click a wire and place a wire label, I've done one already, if you put a name in for the wire, then any other wire that you give the same exact name, there'll be a logical connection between those 2 points, saving you from having wires going all over the place, making it a lot more tidy. So I do that a lot in my designs. So now we're going to implement segment A. Now segment not A, the expression that we had 2 4-input AND gates and 2 3-input AND gates. So if we use an OR gate, that'll only give us the output for not segment A. So we put a NOT gate on the end, and that'll give us segment A. But we can combine those two into a NOR gate, which I'll do later. And these are the 4 binary expressions that we worked out earlier for the value of not A. So we just wire them up. So the output from the OR will be not segment A, because we worked it out to be not A, equals all that. And after the NOT gate, it becomes segment A. So let's just wire it up the way that we worked it out earlier, using our Boolean simplification. D, not C, B, and A, or D, C, not B, or C and not B and not A. I've placed the Y label, called it A, and I've called the 7-segment segment, I've labelled that as A as well, so they are logically connected. So the OR gate gives us not A, and after the NOT gate, that gives us segment A, ready to wire up. Now segment B, which had a 4-input AND gate and 3 3-input AND gates, I'm going to use a NOR gate instead of the OR and a NOT, because it saves us a gate. We don't need the NOT gate now. The expressions for segment B using the NOR gate as shown, D, C, not A, or C, B, not A. So we just wire those up. Not D, C, not B, and A, or D, B, A, or D, C, not A, or C and B and not A. And that'll give us, with the NOR gate, that'll give us segment B rather than not B. So we wire that straight up, and I've logically wired it using a wire label and calling it B. For segment C, we've got these 3 ANDed terms going through an OR gate and a NOT gate, or a NOR gate. So that is the output directly to segment C. So let's wire that up. D and C and B, and D and C and not A. Place a wire label, call the segment the same label, and then they're already connected. Same for segment D. Add a wire and a wire label, label it as D, and label the segment D as D as well, and they are connected. Then for segment E, there's our expressions to wire up, and that is the output. We worked out what not E is worth. So once we not that, it tells us what E is, segment E. Not C, not B, A, or not D, C, not B, or not D, B and A. And using the NOR gate, that is segment E, ready to go. Just two more. These just came from the Boolean expressions that we worked out. We just wire them up from the outputs of our counter, which will cycle through all the numbers for us. D, C, not B. And that we need to label, put a wire in and label it as F, then label the segment on the 7-segment display as F as well. And finally G, that was a piece of cake. G, a 4-input and a 3-input AND gate, which are called AND4 and AND_3. So we have not D, C, B, A, or not D, not C, not B. Now we're ready to roll and test it, see if it works. You'll notice that as I right-click the labels on the 7-segment display, I've called them the same as what the outputs are for those logic expressions. I've also labelled the clock wire, and I've labelled the outputs of the counter QA, QB, QC and QD, and I've done that at the counter end, of course, as well. It means that we can just look at the output to simulate without having to see the whole circuit. So I'll simulate 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So we've done it. We've fully decoded a 7-segment display using a hexadecimal number system, something that isn't freely available as a chip. So I hope you found this useful in learning Boolean expressions and algebra and using it on Proteus. And thanks so much for watching, and comment with any questions that you have. Thanks a lot.